Graph neural network have wide application, but it comes with high training cost of hours and even tens of hours on GPUs. This video introduces our project on GNN training acceleration through a fast and framework-compatible sparse matrix GPU kernel. Let's start with what computation GNN involves. In GNN, every node in the graph carries a feature vector, and iteratively, each node would gather the features from their neighbors and do an aggregation to get a new feature, and also it would do feed-forward transformation on it. Feature aggregation as a fundamental building block of GNN has a poor implementation in current systems, taking up less flop count but even consuming more time than dense matrix multiplication. Our solution is kernel optimization. We formulate feature aggregation as a sparse dense matrix product, which is an SpMM. We design a fast GPU kernel and integrate it in training frameworks, which is more lightweighted than a hardware accelerator solution. So, why feature aggregation is SpMM? Here we see a node gathering its neighbors' features and add them together. This is the inner product between a row in the adjacency matrix and the feature matrix. The adjacency matrix is often sparse and stored compressed, like in the CSR format. Current SpMM kernels either have inconsistent sparse format with GNN framework, so if utilized would bring data transformation overhead, or their performance is not satisfactory. On the usability side, we prototyped our SpMM consistent with GNN framework, which helps us integrate it into two frameworks. On the performance side, we propose solutions for two challenges. First is redundant loading of the sparse matrix, which does not exist in the well-studied SpMV problem, but appears once we make parallel threads to do multiple SpMVs, because those threads always request the same element in the sparse matrix, causing a broadcast-like access pattern to sparse matrix elements. We propose Sparse Row Caching, which first loads a tire of sparse matrix element into a shared memory buffer, sync these threads to avoid any data race, and then make these threads traverse the elements, but from its fast scratchpad memory. If the dense matrix are even wider, sharing sparse elements among too many threads still bring large synchronization overhead, so comes our second design, which is workload merging. Now the second challenge we deal with is workload imbalance brought by the varying length of the sparse matrix rows. Previous algorithms directly distribute threads to rows potentially imbalanced. We propose another scheme to distribute non-zero elements to threads evenly. We adaptively choose these algorithms based on a row length variance. Evaluation results on snap dataset show speedup across problem size and different GPUs. On the models with custom feature aggregation not supported by CoSparse, our end-to-end speedup is even more exciting. For more information, please refer to our prior SC 2020 paper and our code. I am Gu Yue from Tsinghua University, and you can contact me through email. Thank you very much for listening.